A great evening to everyone present here. I'm Aditi Bobri, and I welcome you all to this webinar on nanotechnology, which is organized by DG Saksham. I would like to extend a warm welcome to our chief guest, Dr. Sushil Kumar Jain, sir, who would be guiding us today. Talking about the event, this event is organized by DG Saksham. DG Saksham is another initiative of SEMS Welfare Foundation and has developed content for over 300 courses in multiple languages, which range from 4 hours to 6 months in various sectors of IT, BFSI, retail, and entrepreneurship for all age groups. Our main body, which is SEMS Welfare Foundation, is a professional not-for-profit company and has recognition as Best Service Award for significant national contribution from ITS Education Group. Moving further, this webinar is mainly focused on the basics of nanotechnology and its properties and applications. As we all know, nanoscience and nanotechnology are the study and applications of extremely small things and can be used across all the other science fields such as chemistry, biology, physics, material science, and engineering. We'll also understand the nanoscience and nanotechnology in daily life, how we can synthesize nanomaterial and what are the properties and its application. So let's grab more information about this. To enlighten us on this topic, we have Dr. Sushil Kumar sir with us. He is an associate professor, was a formal HOD physics, and presently working as a director at Manipal University, Jaipur. He completed his PhD from University of Rajasthan in 2006 and qualified competitive examinations for lecturerships like UED, SET, and GATE. He has also successfully completed two collaborative research projects of BREC, BARC Mumbai and University of Rajasthan during his PhD tenure. He has 17 years of teaching and research experience. He has published 31 research papers in national and international journals and Scopus Index and conference proceeding. Dr. Chen has also completed 11 MOOC courses from different universities on Coursera and via LI Network. He has also completed various short-term courses and has attended several conferences, workshops, and seminars. He is the author of 5 books and conference proceeding. He is one of the author in lecture notes in electrical engineering Springer Conference series. Dr. Jin organized 26 conferences and workshops as a converter, coordinator, and organizing committee member. Dr. Jain is a life member of Indian Physics Association Jaipur, life member of Material Research Society of India, and IEE senior member. Dr. Jain also served as a reviewer and session chaired in 17 national and international conferences and DAE's symposium. Now, I request Dr. Sushil Kumar Jain sir to guide us on this topic.
Yeah, thank you, Aditi. So, I am Dr. Sushil Kumar Jain. I am Associate Professor Senior Skill in Department of Physics, Manipal University, Jaipur. So, this is the Manipal University, Jaipur beautiful campus. It is in Jaipur, right? So, Jaipur, it is in Rajasthan. Okay. So, before going to start my talk, I just introduce the Manipal University and its campuses, and then introduction to nanotechnology and my research work, that is structural and magnetic properties of transition metal doped semiconducting nanomaterials synthesized by soldier root. So this is the Manipal University Jaipur. This is the overview of this. So the founder of Manipal Education and Medical Group is Dr. TMA Pai, and is awarded by Padma Shri. And his statement is given individual professional education, and you have given in a lifestyle. So he was visionary, philanthropist, physician, educationist, and the banker. And the legacy continues. The illustrious son of illustrious father, Dr. Ramdas Pai and Dr. Ranjan Pai. So Manipal Group have different institutes at global footprint and Indian presence. So we have the Manipal at Malaysia, Nepal, Dubai, Antigua, and the Singapore. And in Indian presence, we have Manipal University Jaipur, we have Manipal campus at Mangalore, Sikkim, and the Jaipur. So these are the map. Here you can see the different location of Manipal University, Jaipur, Manipal University campuses. So this is Manipal Group in Education. Manipal University is established in 1953 and India's first self-financing multidisciplinary university. It has 21 institutes, 16,000 students from 53 countries and 180 courses. And then Manipal Group of Medical Sciences, Nepal, established in 1994, a model of collaboration between the Manipal Group and the government of Nepal. And we have around 1,500 students, over 13% non-Nepali students. Then Sikkim Manipal University, established in 1995, and then Melka Manipal Medical College, Malaysia. We have Mahe Manipal Dubai campus, and then American University of Antigua, Manipal. So this is our beautiful campus, Manipal University, Jaipur. The land for this is 66.67 acre, land for hostel and staff, 54.65 acres land. So this is at the heart of this Jaipur map. So here you can see the different location of visiting place of Jaipur, like Jal Mahal, right, Hawa Mahal, and this Amer Fort, and you can also see the Manipal University beautiful campus. So this is our management. Dr. K. Ramnayan is the chairperson, Manipal University, Jaipur. Our Honorable President, Dr. G. K. Prabhu, and then the Honorable Professor Dr. Anand Sharma, Pro-President, Manipal University, Jaipur. So this is our beautiful campus, infrastructure at MEJ, you can see. So these are the facilities we have available at Manipal University, Jaipur, and this is also known as Central Analytical Facilities. So in this, we have Fourier transform, infrared spectroscopy, UV visible spectroscopy, photoluminescence spectrometer, thermogravimetric analysis, जिसे हम बोलते हैं TGA. Okay. So by using this Fourier transform infrared spectroscopy, you can study the infrared spectrum of absorption and emission of a solid, liquid, or gas. In UV visible spectroscopy, we use light in UV visible and visible region. And by using this UV visible spectroscopy, we can find the energy band gap of any material. Okay. And the third is photoluminescence spectrometer. So by using the probing of the electronic structure of material, we can identify the optical properties of any material by using photoluminescence spectrometer. Then thermogravimetric analysis. By TGA method, we can thermal analysis in which the mass of the sample measured over time as the temperature changes. And we also have scanning electron microscopy, by which you can get the two-dimensional and three-dimensional study of any material. Microscopic study can be done. Then we have atomic absorption spectrometer. These are the facilities available at Manipal University, Jaipur. So quantitative determination of chemical elements using the absorption of optical radiation by free atoms in the gaseous state, we can find by using this atomic absorption spectrometer. Then optical contact angle we can get by using this OCA device. So high performance liquid chromatography we can get by using this technique. We can get analytical chemistry used to separate, identify, and quantify each component in the mixture. By gas chromatography, by using this in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. And then gas chromatography and mass spectroscopy, by which we can analyze or separate volatile components of a mixture and separate the different mass also. So these are the facilities available at Manipal University, Jaipur. And by using these facilities, we can analyze in the following way: structure elucidation of organic compounds, environmental, pharmaceutical, petrochemical samples, testing of pesticide, contamination with enhanced, and specialized databases. So these we can find by using these facilities. Oxidative or thermal stabilities of materials, glass transition temperature, transition and reaction enthalpies analysis can be done. Measurements of solar cell, anti-reflective properties, of films and polycrystalline silicon wafers can be measured by these devices, right? So by using these devices, we can analyze these uh, properties of the material. Here you can see this is HPLC device, atomic absorption spectrometer, gas chromatography with mass spectrometer. These devices, these instruments, these apparatus are available at Manipal University, Jaipur, in Central Analytical Facility. So now I'm going to start about the nanotechnology. So this is the introduction of nanotechnology. We will just learn about the basics of the nanoscience and nanotechnology. So now the question arises, what is nanotechnology? So nano means the Greek word for this is dwarf, and which means 1 billionth of a meter. 1 meter means 10 raised to power minus 9 meter is the range. 10 raised to power minus 9 meter is called nano. Okay, and the sense of nanotechnology is the ability to work at the molecular level, or what we can say at atom by atom levels, and we can create large structure with fundamentally new molecular organization but in the nanotechnology. The range of nanomaterial is 1 to 100 nanometer. Okay, and what is the dimension of 10 nanometer is 1,000 times smaller than the diameter of a human hair. So this is about the nanomaterials. So this is the timeline of nanotechnology. So in 2000 years ago, the sulfide nanocrystal used by Greeks and Romans to dye hair. 1000 years ago, the gold nanoparticles of different size used to produce different colors in stained glass windows. So here you can see when you see the gold in bulk size, the color is yellow. Okay, when we reach to the lower level side means nano size range, you will find the different colors of gold. Okay, so this is again the optical properties get changed when we go to the lower level side. So in 1959, there is a plenty of room at the bottom. This is the statement given by the R. Feynman in AGM of American Physical Society of December 29, 1959. And he discussed about the ideas of manipulating and controlling things at the atomic scale. Okay, so what we can do here, manipulating and controlling things means we can arrange atoms at the nano range. Okay, so in 1974, the nanotechnology, the word is given by Tanguchi, uh, uses the term nanotechnology for the first time. And in 1981, the IBM developed scanning tunneling microscope. By using this scanning tunneling microscope, we can you can see the optical properties changes. Tunneling means there is some gap between the probe and the atom, but the signal can be produced. Okay, so this device developed by at IBM. In 1985, the buckyball, you can see here the arrangement of this is a new type of carbon, and here you can see the arrangement of these carbons in the hexagonal and the pentagonal shape. So you can see here, just a minute. So, and I'm just using. So here you can see this is the pentagonal. This is the pentagonal, okay, and this is hexagon. So one pentagon and hexagon. So here we use around 12 pentagonal and 20 hexagonal rings, and that will make a spheroid shape with 60 vertices and the 60 carbons. Okay, so this is the buckyball. So proto, smelly, and curl determine the structure of carbon 60. So here we can produce this carbon 60 by using the different techniques. So here you can see. So here this you are using the target. The target may be a graphite. So what we can do here. This is the vacuum chamber. The laser beam incident on the target, and that will get vaporized. And this vapor we can absorbed by the substrate, and on the substrate we can get this carbon 60 buckyball. Similarly, we can use the different the next technique, that is electric arc discharge method. So here we will use two graphite rod. One will be the anode and another one will be the cathode. And when we bring near to each other, you will get some carbon soot. And in this carbon soot, there will be some carbon nanotube and some will be the this buckyball. So these are the ways by which we can develop the buckyball. So here you can see the two techniques, laser beam and the electric arc discharge method. So the properties of this buckyball is it may be harder than the diamond and maybe more slippery than the Teflon and maybe insulator or conductors. So and the best property of this buckyball is we can storage hydrogen in the case of this buckyball. Okay, so buckyball can enclose an atom of another element inside itself, right? And this is the synthesis of the buckyball. Then in 1986, the Engines of Creation, the first book on nanotechnology, is written by K. Rick Drexler. In 1989, the IBM logo made with individual atoms. So here you can see in this second diagram here, this IBM logo, it is, so this is also known as manipulation of atom at the nano range. So here by manipulation, by shifting the atoms from one place to the another place by the atomic force microscope, so AFM, and this logo was developed in 1989. So IBM logo made with individual atoms. So the shifting of the atoms by using atomic force microscope can be in 1989. Okay. Next is 1991, the carbon nanotube discovered by S. Izima. So here in this slide you can see the electric arc discharge method. So in electric arc discharge method, we will get the buckyball and the carbon nanotubes. So the carbon nanotubes here you can see in 1991, the carbon nanotube discovered by S. Izima, and the carbon nanotubes are formed by a layer of hexagonally arranged carbon atoms rolled into a cylinder. So what you can do, you take the graphite layer and you add end to end point, then you will get a tube like structure that is known as carbon nanotube. Okay, the diameter of carbon nanotube is 1 nanometer, and the carbon nanotube length can be a million times greater than its width. So the nanotube can be a single walled nanotube which have 1 to 2 nanometer diameter, or multi-walled. Multi-walled in the second diagram you can see here, this is multi-walled nanotube. Okay, in the one single wall nanotube you will find one more nanotube, and this is also known as multi-walled nanotube. So how we will develop this multi-walled nanotube in the electric arc discharge method? So here we will use some catalyst. Okay, so in the presence of catalyst we will get the multi-walled carbon nanotube. So in 1999, the nanomedicine, the first nanomedicine book by written by R. Freitas. In 2000, this National Nanotechnology Initiative launched with a large amount of fund in the budget provision. So this is overall about the nanotechnology timeline. So it started from 2000 years ago, and today we are also working on some nanomaterials which can provide a better optical, magnetic, electrical properties. So here you can see the range of the things which is get natural and the things which is man-made. So here you can see the size of ant is 5 mm to the size of atom of silicon, that is 10th of nanometer. You can also see the size of DNA, that is 2 to 12 nanometer diameter. Okay, then the 10 nanometer diameter of this we can say the cell structure can also be this size. Red blood cells is also 2 to 5 micrometer. Human hair is 60 to 120 micrometer wide. So here you can see the range of the things which is natural made, right? So here we can compare the structure of nanomaterial, the size of nanomaterial nearly equal to the DNA, that is 2 to 12 nanometer in diameter. So here the things which can be made by man. So head of a pin is 1 to 2 mm. You can see here. Okay, micro electron mechanical MEMS devices, that is again 10 to 100 micrometer wide, right? So in the nanotube electrode, we generally have 1 micrometer structure. Carbon nanotube, we have 1.3 nanometer diameter, right? Buckyball, which is on 1 nanometer in diameter. Okay, so this is the things which is man-made things and the natural things. Here you can see the different range. So both the natural as well as artificial world can now be categorized by in two design, micro world and the nano world. And then we can starting from the DNA to the human hair. And similarly, man-made world is now shifting from its attention from micro to the nano scale structure. So there are actually these are about the nano materials is range. What is the range of nanometer? The range of nanometer is from 1 nanometer to 100 nanometer. Okay. So there are two approach by which we can get the nanomaterials. There are, that is top-down approach and the bottom-up approach. So here you can see in the first diagram, this is the top-down approach, and in the second diagram, this is bottom-up approach. Okay. So in top-down approach, generally a bulk material is taken. Okay, we will take a bulk material and then machine it and modify it into the desired shape and the product. So here you can see one example. In the bottom up approach, so in the bottom up approach, we build something from basic materials. So here the chemical composition, chemical reaction is also a bottom up approach. To build something from basic materials and assemble them from the atoms, and therefore very important for fabrication. So what we can do here in the chemical synthesis process, we will take different chemicals, and by this chemical reaction, we will get the final product. So that is the bottom-up approach. Okay. So what is the difference between the top-down and the bottom-up methods, and what are the techniques which is included in top-down and the bottom-up approach? So here you can see the difference between the top-down and the bottom-up approach. But in this, what is the top-down approach? The top-down approach is lithography, deposition, etching, machining, and ball milling. These are the techniques where we generally have a bulk material and machined it and modify into the desired shape and the product. So these are the techniques, that is lithography, deposition, etching, machining, and ball milling. So in ball milling, what we do generally, we crush the powder and making it in a nano size range. Okay. So these are the top-down approach. In bottom-up approach, we generally have chemical synthesis, self-assembly, plasma etching, and the chemical vapor deposition. Okay, so whatever the material we have, we vaporize it and then we will take on the substrate. Okay, so that approach is bottom-up approach. So there are different properties once we see the bulk material. Okay, and when we reach to the nano size range, the properties also change. So nanoscale size, what are the effects when we reach to the nanoscale range? So these are the properties. Number one is physical properties that also get changed. Generally in physical properties, we may consider, let us take the melting point. So this we will take one of the example, what will happen when we reach to the nanoscale range. In the chemical properties, we generally have the reactivity. So what happen when we reach to the nano size range, what effect we observe in the chemical properties. And the third is electrical properties. So what happen when we reach to the nano size range, the resistivity, or what we can say the conductivity of the material. Next is mechanical properties. So we will also see these properties, mechanical properties, optical properties, and also we can also see the magnetic properties of the material when we reach to the lower size range. So nanoscale, what are the nanoscale size effect? So here you can see. So the demonstration of novel phenomena and properties that including changes, and the first properties is physical properties. So what happened? What happened when we reach to the lower size range? So in this diagram, you can see the atom which is inside and the atom which is at the top. Okay, so which is tightly bound. So here with the atom which is inside, it is surrounded by the other atoms also. Okay, but the atom which is at the surface, it is less bound. Okay, so what will happen when we give some thermal energy? So it will, it will, it will be out. Okay, the bonds will break. It will be out, and the melting point will get decreased. So the smaller a solid object gets, the larger the percentage of its atom residing at the surface. So here we can see the smaller a solid object gets, the larger the percentage of its atom residing at the surface. Inside a crystalline solid, the atoms are constrained by the crystal lattice, but at the surface, the atoms have more freedom to move. So here you can see this atom have more freedom to move compared to the atom which is inside. Okay, so as the temperature increases, they begin to vibrate. Okay, so when the vibration of the surface atom reaches a certain percentage of the bond length between them, the melting begins and then start to propagate throughout the solid. So what happened here, the surface atom require less energy to move because they are in contact with fewer atoms of the substance. So in nanoscale size means, the nanoscale size means, let us say this is your one atom. Okay, let us say this is one atom. Okay, so now what we are doing here, we will increase the surface ratio. So what do we mean by this? So we will divide this atom or can say this size into this cube into the two cubes. So what will happen here? The surface area will also get increased. Now we will divide into 4. Okay, so again the surface area will get increased. So a nanoscale range means the more surface area compared to the volume. So here the volume remain fixed, but the surface area get increased. Okay, so this is the nanoscale size effect. So what happen for the chemical properties? So reactivity get increased. How? The surface atom possess more energy than the bulk atoms, and consequently surface atoms are more chemically reactive, and the nanoparticle possess enhanced chemical reactivity. So this is uh, one of the property which get increased. Then the electrical properties, so conductivity get increased. So what do we mean by this tunneling current? So you all know in the physics. So when the energy of the particle is less than the barrier height, but it uh, uh, transmit to the gap. Okay. So here the energy of, so that is also known as the quantum tunneling. Okay. So at lower size range, what we will observe the quantum tunneling effect. Okay, so the resistance will get decreased and the conductivity will increase. So at the nanometer scale, the electric insulator begins to fail to block current flow. So electrical insulator just begin to fail the block of current flow. So current will get transmitted, or we can say the electron will transmit it. So quantum mechanical effect is known as tunneling, and the tunneling current increases exponentially as the thickness of the insulator is decreased. So we all know that the transmission coefficient T. So this transmission coefficient is equivalent to the exponential minus of 2kL. Okay, exponential minus of 2kL. So what is K? K is propagation constant. L is the width of this barrier. Okay, L is the width of this barrier. And then secondly, the band structure begins to change when metal particles become small and discrete energy levels begin to dominate and Ohm's law is no longer valid at the lower size range. Then the next property is mechanical properties, and that is again known as strength. So at the nanoscale, surface and interface forces becomes dominant. So let us take the example in adhesion force, capillary forces, and strain forces. So these forces can exceed forces that are normally dominant at macroscopic length scale. So surface coating are extremely important to prevent sticking in the nanoscale electromechanical system. So these are the mechanical properties. So the strength will also get increased in the. So one of the example we have seen in the buckyball. So that is also have more strength compared to the metals. So optical properties, again, the light emission or the color, we also say the color will get changed when we reach to the nano size range. So small particles absorb light and leading to the some color, and this is the size dependent property. So one of the example is gold, which is readily forms nanoparticle but not easily oxidized and exhibit different colors depending on particle size. So now the question arises, why do property changes? Okay, so there are the four important ways in which nanoscale material may differ from the macroscale materials. Number one, it has greater surface to volume ratio. So you can see the different properties of nanomaterials and why these properties get changed. So number one is greater surface to volume ratio. Number two, gravitational forces become negligible and electromagnetic forces dominating. Okay, so when the particle size is very small, atomic size range, these gravitational forces become negligible. Okay, next is quantum mechanics. So when the particle size is very large, we use classical mechanics for them. We will get the energy and the position of the particle in the classical mechanics for the larger particles. When we discuss the nanomaterials, we generally use quantum mechanics. So quantum mechanics is the model used to describe motion and energy. So you all know the Schrodinger equation we generally use for the material which have nano size range. Okay, by using Schrodinger mechanics, by using Schrodinger equations, we can get the position and the energy of the particle. Okay, then random molecular motion becomes more important at the lower size range. So here I am just going to demonstrate the work which I am doing this time. So this is the synthesis, structural characteristic, and the magnetic behavior of 3D metal doped semiconducting materials. So what we are observing here, why we are using 3D metals. So generally, when you see the periodic table, these D metals have the unpaired electron in their outer orbit. Okay, so in the valence shell, they have unpaired electron, and that unpaired electron can produce different properties when we dope these three metals in the zinc oxide, in the tin oxide, or in the titanium oxide. So optical properties get changed, magnetic properties may also get changed when we dope these 3D metals in the semiconducting nanomaterials. So here I am just going to present how we have developed these 3D nanometals. So that is also known as synthesis. And for the structural characteristics, we have used the X-ray diffraction and the scanning electron micrograph for the microscopic study. And for magnetic measurements, we use vibrating uh, magnetometer. So here these are the methods of nanosynthesis. So there are different methods, physical methods. In physical methods, we generally use carbon arc, laser ablation, and ball milling methods. In the chemical methods, so here I am using these chemical methods. Okay, so in the chemical methods, we generally use the reactant 1 and reactant 2, and by using temperature, pressure, and the time, we got the product, right? So there are different chemical methods. So number one is sonochemistry, microsynthesis, hydrothermal methods, microencapsulation, sol gel methods, wet chemical co-precipitation methods. So these are the different methods by which we can develop the semiconducting nanomaterials. So here we are using the sol gel methods. Okay. So what is sol gel method? This is a chemical solution deposition technique and starting material from a chemical solution, and we generally take the alkoxides, leads to the formation of chloride cell suspension, that is also known as sol, and the removal of the liquid phase from the sol, we will get the gel, and the particle size and shape are controlled by the sol gel transition. Okay, the thermal treatment. So for the thermal treatment, what do you mean by thermal treatment? That is known as calcination and firing of the gel, that leads to the further polycondensation reaction and enhance the mechanical properties of the products, that is oxide nanoparticles. So here you can see the sol gel technique. So we are using this method. Okay. So what we are doing here, we will take some starting material, and that starting material dissolved in the water, and this process is known as hydrolysis. Okay. So what we will get after dissolving these precursor in the water, we will get the sol. Okay. Now there are different methods, that is spin coating method. So by spinning or dipping or spraying, we will get the material um, on the substrate in the gel form, and after calcination, we will get the thin film. So this is the first method by which we will develop these nanomaterials and in the thin film form. Then by the hydrolysis and then alcoholysis chemical reaction and the deposition within porous matrix, we will get gel. So here you can see the freestanding nano rods wire. So here we generally use the porous matrix in which we will pour this gel, and then we will get the freestanding nano rods and wires. Similarly, we can use the different methods. By using the calcination process, we will get the material in the powder form. Then when we will get the sol, then after agglomeration, means we will put the material within for 2 to 3 days, then the agglomeration, and after dehydration we will get the sol in the gel form. So by this gel, by slow drying of the gel, we will get the zero gel, and then after calcination, we will get dense ceramic, and by rapid drying, we will get this aerogel. Okay, so these are the different techniques of this sol gel method. So here you can see in the first process, here you have seen the spinning, dipping, and spraying. So how it is possible? So here you can see the different techniques. That is, number one, aging. Aging means you put for a long time, and this is deep coating method. So here, what you will do, you will take some substrate and you dip in the material, dip coating, to and fro movement we will do here, and then we will take we can also do the spray coating. So here you can spray the material on the substrate and you put some heater here. Okay. So this is another method, that is spray coating method. And the next is here you can see the dispenser. So it is the dispenser, and this is your sol, and this is your substrate. So by spin coater, we will spin this substrate, and after annealing of the film, we will get the required film. So this is the sol gel method uh, by which we can develop the nanomaterials. So there are different advantages and disadvantages of this technique. So what are the advantages? The large area scale, maybe we can develop these nanomaterials. This is precise composition control. Okay, low temperature synthesis ये आपके पास होता है. So high homogeneity, and it is easily achieved. Okay, and what are the disadvantages of this technique? It is sensitivity for the atmosphere condition, expensive of raw materials, and use of toxic solvent systems. So why is 3D metal substitute in zinc oxide and tin oxide? So 3D metal dop zinc oxide and tin oxide. And why we are doping here? We want to showcase here the properties of zinc oxide and tin oxide, that is diluted magnetic semiconductor. So what do we mean by this? Zinc oxide and the tin oxide at room temperature generally they are they are non-magnetic. Okay, so once we dope these 3D metals in zinc oxide and tin oxide, so what will happen? The material properties get changed, and at room temperature they shows the ferromagnetic behavior, and this property we can use in spintronic applications. Okay, so here one more thing is the 3D metal substitute zinc oxide and tin oxide has a lower cost, and when compared to the actual available material like gallium nitride, aluminum gallium nitride, cadmium telluride for similar application. So these are the experimental details of how we can develop this zinc oxide. So generally what we have chemicals that is in 1:1 molar ratio. These starting materials we generally have, let us suppose I want to develop zinc oxide, okay, in which I want to put the silver and the cobalt. So here you can see the final product is zinc 0.9, Az 0.005, cobalt 0.05. Okay, so in this synthesis technique, we don't require a very high temperature up to 300 degrees centigrade. When we keep our sample 3 hours, we will get this zinc, silver, cobalt oxide powder. Similarly, we can also get the titanium, silver, cobalt powder. So once we develop these materials, okay, so that is known as synthesis process. So after synthesis, what we have to do, we have to find out that our material is developed or not. Okay, our material is synthesized or not. So for that, what we will do some structural and for structural measurements. And these structural measurement is the X-ray diffraction. Okay, so what we will do here for the crystallinity and the structure of zinc oxide particles, for the determination of crystallinity and the structure of zinc oxide particle, we will use X-ray diffraction. And what is X-ray diffraction? We generally using copper K alpha radiation. So 0.15418 nanometer it has wavelength, and this device means X-ray diffraction spectrometer. We generally use 40 kilovolt and 35 milliampere, and the range of is 0 degree to 75 degree. And the morphological analysis of the sample that is carried out by SEM, that is scanning electron microscope, and this is made by Colgis, and this is the model number. Then the magnetization measurement of 3D doped zinc oxide that is carried out by SQUID, that is quantum design make model, and an external field up to 10 kilorasted in the temperature range 5000 to 5 Kelvin to 300 Kelvin. And the measurement was also made in the field cooled mode and the zero field cooled mode. So what happened? What do we mean by field cooled and zero field cooled mode? Mode in field cooled mode, the sample is cooled from 300 Kelvin downwards in the presence of a measuring field, and then movement is recorded either in this cooling cycle or in the warming cycle. So this is the characterization technique, X-ray diffraction technique, and scanning electron microscopy. So here you can see the how this X-ray diffraction work, how these X-ray diffraction X-ray diffractive spectrometer works. So here you can see this is the X-ray diffractometer. So what we will do here, we will put our sample here, and when the X-ray incident on the sample, it will get diffract. And so let us suppose if you put a theta angle incident ray X-ray at theta angle, then we will put detector at 2 theta angle. Okay. So what we'll find here, the intensity when we take the intensity versus angle curve. So you will see here this is 2 theta versus intensity curve. So what do we mean by these intensity? Intensity means the light, the X-ray get diffract from the plane. Okay, so let us suppose if we have 001 plane, so we will get this peak. So once the X-ray diffract from the plane, you will get these peaks, and uh, when not diffract, you will get this background. Okay, so here you will get peaks for different planes. Okay, so the scattering of X-rays from atoms produces a diffraction pattern and which contains information about the atomic arrangement within the crystal. So for the amorphous material like glass, we don't have a periodic array with long range order. So you all know about the glasses. The glasses have does not have the crystalline structure. So we don't have a periodic arrangement of atoms in the amorphous material. So we don't produce any diffraction pattern. Okay, so their X-ray scattering features broad, poorly defined amorphous humps. Okay, you will see hump. So here you can see once again, this is the X-ray diffraction 110 plane, 102, 111, 200. These are the planes on which light get diffract, and you will see these peaks. So you all know about the Bragg's law. This is lambda is equal to 2d sine theta, where d is the interatomic distances, lambda is the wavelength of the X-rays which you are using. Sine theta is the angle, and this is the form factor, intensity versus form factor. So here we can see the results and results for our samples. So this is the zinc oxide sample. So when we dope manganese and iron, you will get this pattern. When we dope manganese and cobalt, you will get this pattern. So here you are observing here the peaks are same for all the materials. So what we are observe here. So when we dope manganese and iron, manganese and cobalt in zinc oxide, they will get occupied in the zinc sites fully. Okay. So these are the different properties, different formulas by which we can get the values like d, the interplanar distance we can get by using this formula number one. Okay, uh, you can also get the volume of unit cell. You can also get the atomic packing fraction. You can also get the bond length by using this formula. Even you can also get the particle size by using the device sharer formula. So what will be the particle size of the materials? So we are using this device sharer formula where this T thickness is the particle size, K is the shear constant, lambda is the wavelength, and beta is the full width at half maximum in the X-ray diffraction peaks. Okay, so this is the formula by which we can get the particle size of our material. So what we are observing here, the range of our particle is from 20 nanometer to 28 nanometer, and that is indicating the nanocrystalline nature of the sample. So um, we can also get the particle size by using the William Hall analysis. So this is the formula: beta post theta is equal to 0.9 lambda upon L plus 2 epsilon sin theta. So this is the William Hall analysis by which we can get the particle size of our material. We can also get the dislocation density. We can also get the orientation parameter by using X-ray diffraction. Then we can use single electron microscopy. So this is your single electron microscopy. Uh, how it is designed. So it is electron gun. From this electron gun, you will get some the electron beam, and here we will use some anode. So this electron will get accelerate, and then we will use some magnetic lens. So these are the magnetic lens. Okay, so this X-ray, this electron beam incident on this. This is our specimen, or we can say sample. So these electron beam get diffract, and by using this secondary electron detector, we can detect the signal. So this is the single scanning electron microscopy. So scanning electron microscopy is a type of electron microscope that produces images of a sample by scanning the surface with a focused beam of electrons. So here you can see the scanning of the surface of the atoms or some specimen, you will get the signal. The electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and the composition of the sample. Next is that is again known as transmission electron microscopy, and this here what we there are some changes in the geometry. So in the scanning electron microscopy, the sample is here, okay, but in transmission electron microscopy, we are using the electron which get transmitted from the specimen. So what we'll do here, this is the electron gun, this is our anode, this is the condenser lens, okay, and this is the specimen. Now the electron get transmitted. So by these transmitted electron on the fluorescent screen, we will take the images of our sample. So the transmission electron microscope can image specimen up to 1 micrometer in thickness. The transmission electron microscopy uh, is a microscopy technique in which a beam of electron is transmitted through a specimen and form an image. So these are the scanning electron micrograph of zinc oxide. So here you can see the clustering of particles that occurred on the surface, and also you can see here the irregular size of our materials. So again, the tin iron oxide. Okay, this is the scanning electron micrograph measurements. So here, what we are observing in my sample in the magnet for the magnetic measurements. So a number of studies have been reported to exhibit room temperature ferromagnetics in manganese, iron, cobalt, or zinc oxide, and we have studied the magnetic behavior after doping 5% manganese and 5% cobalt in zinc oxide, and another sample in which we substitute 5% manganese and 5% iron. So we have seen that the effect of manganese and cobalt both and manganese and iron both in our zinc oxide samples. So here you can see the magnetization measurement of zinc oxide at 300 Kelvin and the 5 Kelvin. So we are using the 100 Oersted. So what you are observing here at room temperature, the material is non-magnetic, and at 5 Kelvin here the zinc oxide where we dope manganese and iron, it is at 5 Kelvin it is ferromagnetic. But in case of 5% manganese and 5% cobalt of zinc oxide, what we are observing here, we at room temperature, we have seen some magnetic behavior. Means we have seen some magnetic movement of the material. Okay, so this is the charge and the spin of the electron. This is um, the practical application of this material is spintronic application. So what do we mean by spin? Generally, charge and the spin of the electron lead to a new magnetic and transport properties, and that is known as spintronic. Generally, what we are when we are making devices, we generally use the charge or rotation of the electron, but in spintronic devices, we generally use the spin of the electrons also. So here you can see the April pull and zero April pull measurement of this sample. So here you can see. So when we dope this transition material in the zinc oxide or 3D metals in the zinc oxide, we will observe the room temperature ferromagnetism in the undoped doped zinc oxide. So these are the references. So here I have one video for this nanotechnology.
Nanoscale motor, and it has bushings and all kinds of little pieces inside there that is built very differently than the way we make things, so that they can participate in that debate in a meaningful way.
So in this video now you can understand the applications of the nanomaterials, where we can use these nanomaterials in the medical applications, in the in for the photovoltaic uh, cell, and in also in the sports field we can use these nanomaterials. So this is overall about my talk. So what we have started from the nanotechnology, and the range of nanometer is from 1 nanometer to 100 nanometer, and there are various techniques by which we can develop, we can synthesize nanomaterials, that is sol gel, laser ablation, and then carbon, this electric arc discharge method. So there are various methods by which we can develop nanomaterials, and the nanomaterials have like carbon nanotube, buckyballs. These are the materials which we can develop, and these materials also have the various applications. Then we had also understood now about the properties, nano materials properties like mechanical properties, optical properties. So once we reach from bulk material to the nano size range, the property of the material get changed, and due to the surface to volume ratio increases. Number one, number two, the gravity effect get reduced. So this is about overall about the nanomaterials. Okay, if you have any query, you may ask.
It was discussed earlier that soil gel method is sensitive to atmosphere. What parameters have been put into the place to make sure it will not affect the synthesis of the nanomaterial? Like, is the environment monitored before proceeding to the soil gel synthesis?
Yeah, this is also a great challenge for us, because if the particle size are very small, then it may also go through from our inhaling system, and it can reach to in our body. It may create problems in our lungs. So this is again the challenging uh, to developing of the nanomaterials.
Mukesh is asking, can we be first applied medical because the life of human is very important?
Yeah, if your sample is properly made uh, and is in nano size range, so first we have to observe the properties, then we can apply in the human body. Okay, so once we develop the material, then we have to characterize, we have to check their properties, and then we can apply. Directly, we can't apply these nanomaterials. Okay, it may also harmful to our body. Okay,
What are the ways can be a nanotechnologist?
nanotechnologies can be in physics, in chemistry, in bio. So nanotechnologies is everywhere in this time. So after, let us suppose if you are doing BTech, so after BTech you can select this nanotechnology in your PG program. So you can go whenever you want in this field. Okay, and from BTech to you can go to in nanotechnology field from after MSc or after BSc. You can you can be a nanotechnologist.
Mukesh is saying that he has heard it that it is very useful for cancer like life-threatening disease cure.
Yes, yes. So what happen? These nanomaterials, when we inject in the body, they will destroy all these bad cells of this cancer. So it is very useful in the medical applications also.
Okay, Farah is asking, are the homeopathic medicines are nanotechnology products?
Homeopathic.
Homeopathic medicines are nanotechnology products.
Yeah, the research are going on in this field also. Uh, it may be one example I can give you. So when we take a sugar, okay, so take a sugar and you paste it and make it powder. So and you take the test of that sugar. So what you will observe, when you press or when you crush powder in your mouth, it will reach, it will be more sweety compared to the one crystal of sugar. So when we crush this sugar, it becomes in powder form, and it, or what we can say, it will be in the size will get decreased of that nano that sugar, and it will cover the more area. So we will get more taste, or that sugar, when it is in powder, it will be more sweety than the crystal. So the research is going on.
Dinusha is asking, can this technology be a part of lawyers?
Lawyers, yes, why not? Because the nanotechnology also impacted on the environment. So the lawyers can also participate in this.
Okay,
Like one example we can give, when this plastic, we all know about the plastic. So when the plastic was developed, the scientists get this Nobel Prize. Okay, at that time. So what happened now? We are totally frustrated from the plastic. So we want to dissolve the plastic, but we don't have the techniques this time to dissolve the plastic. So sometimes the lawyer is required to, uh, let us suppose we are developing nanomaterials, toxic nanomaterials, and we are going to harm our environment. So the lawyer can judge um, that this is not a right way now. So this is overall about, lawyer can also be participate in this uh, the invention of the nanotechnology, in my view.
okay, one more question. Do some beauty products are the product of nanotechnology?
Yes, yes, why not? Zinc oxide is also used in the beauty product. So these beauty products is also a nanomaterials. So you can see, um, in beauty products, we use nanomaterials. In medical applications, we use. So everywhere we are using this time nanomaterials. Even on the car body, we can coat it with nanomaterials. On our glasses, when we coat it, so you can see different color of our glasses. So where we use different nanomaterials coating on the glass, so you can see different colors this time. So everywhere we can use the nanomaterials, but the synthesis and the characteristic properties we have to see. Synthesis and the characteristic of the nanomaterials we have to investigate in the proper way.
Again, question is opportunities of nanotechnology.
So there are various opportunities. Opportunity means the field where you can, or so you can also go in the material science field. After BTech, you can do MTech. After BSc, you can do MSc in nanotechnology. After MSc, you can reach to the research labs where you can do PhD in the nanotechnology field. So there are various opportunities. You can also teach students. You can develop materials in the industries. So this is overall.
One more question. In this time of pandemic, how can nanotechnology help?
right? So you can see one of the example for this COVID. For this COVID, what we can say, this is again the virus. So DRDO, means Defense Research and Development Organization, they have developed some medicine. That medicine reached to this COVID virus and make some bond. So what is here? Here they have used the nanomaterials which can bond this COVID virus and it cannot spread in our body. Okay, so I think they have also used these nanomaterials or nanotechnology in the COVID pandemic situation.
One more question. Are there any options for LLB graduates for this field to become a technologist?
Yes, they have to search regarding the laws which impact on the environment. Number one, because we have one of the drawbacks of this nanotechnology, the impact on environment. So they can see some laws which belongs to the environment, industries law. They can also see. So I think they may also join uh, the nanotechnology industry because they have to take consultancy from them also. Yes, graphene
One
is
question.
yes, graphene is one of the example of the nanomaterials.
I, on behalf of DG Saksham, would like to thank Dr. Sushil Kumar Jain sir for his guidance. And thank you each and everyone for attending this webinar. I'm sure everyone has got to learn a new thing today, which would definitely help them in future. Thank you everyone, and we look forward to seeing you at the next events as well. Thank you.
Yeah. Thank you, Aditi, and thank you all the participants for joining this talk. Thank you, organizers. Thank you.